Hello, everyone. I'm Ufuk Erol. I'm PhD student in Communication System Networks research group called CSN. Today, I'm going to talk about constraint device networks and time-slotted channel hopping, which is used for scheduling on the Mac layer. So the main challenges in the constraint devices networks are the battery. The first thing is the battery. Since the devices are battery powered, after they are deployed, they used to stay without any connection as long as possible. So improving the battery performance gives a big improvement in the network. The another problem is the communication range. Communication range is depending on the technology and the frequencies used. For 2.4 gigahertz radios, the range changes between 50 meters to 200 meters, depending on the output power, and the data rate is changed depending on the configuration. The other challenges are the interference. External interference, since we use 2.4 gigahertz and sub-gigahertz ISM bands, they are prone to the interference by other technologies. So it is crucial to eliminate that external interference in the network. The other one is multipath fading. The multipath fading is caused by the waves and bands. The signals can collide with other objects when they have metallic things around, so they can change the phase of the signal, and then they can basically destroy the signal itself. So as you can see, this is the Internet of Things protocol stack, which is specific for 6-dish Internet protocol, 6-dish Internet of Things protocol stack. As you can see on top, we have a web-based application layer, and then we have integration layer, which is 6LoWPAN, which is used for fragmentation and defragmentation of the packages. Since we use IP version 4 frames and then IP version 6 frames. IP version 6 frames are long, very big frames to process at the .15.4 standard. So we just fragment these frames. So as you can see, there's a gap in the scheduling. IEEE has a specific standard called time-slotted channel hopping. So channel hopping introduces to create a scheduling, but it doesn't really specify how to create the scheduling and then to process it. So my specific research is in that area. As you can see in the slide on the left, a very simple topology. So in that topology, every node knows when to wake up and when to go back to sleep. So in that case, what we do is we try to optimize the energy efficiency, and we try to not lose any frames due to collision. So in that networks, every node knows when to wake up and when to go back to sleep. We use synchronization frames to arrange that capability in the network. As you can see on the screen, we have 5 or 6 different time slots we use. So we try to keep the energy consumption at the lower level as much as possible. So each node knows when to wake up and when to go back to sleep due to the synchronization in the network. So if the node doesn't have to receive an acknowledgement, so it just activates the radio in a specific time to receive the data and then goes back to sleep. In other cases, if the node needs to receive an acknowledgement, it stays active, the radio, the whole time to receive the acknowledgement and then send the data as well. So there are different scenarios, and there are different ways of establishing the network itself. So the most common and the nowadays people use mostly 2.4 gigahertz links. So 2.4 gigahertz links, they have specific range and then specific data rate, but it causes bottleneck problem when you get close to sync node, as you can see on the left side. So when the data aggregates, which gets close to the sync node, we see lots of drops due to the bandwidth of the radios. So on the right side, as you can see, I apply sub-gigahertz radios as well. So I combine 2.4 gigahertz and sub-gigahertz in a single node to give extra capability to the node itself. So as you can see on the upper left-hand side, or on the multi-radio network, the network can have multiple thousands of nodes that can connect the backhaul node, which can process the information to the SIG node, which is kind of backhaul part of the network. So it can use two bands, which is 2.4 gigahertz and sub-gigahertz links. So the advantage of sub-gigahertz links, as you can see, I crossed it with the red cross. So they can reach further distances. So in that case, we don't have to deploy more radios nodes to process the data, to forward the data. What we can do is we can just eliminate that sub-gigahertz radio, which has short range, and then we can use the longer range of the sub-gigahertz. Another advantage of using that is the radios can work simultaneously to process the data. So each node doesn't have to wait for the next slot frame to process the data. So they can use both radios to process the data at the backhaul. So it just gives extra bandwidth, and it just gives extra capability to the network. We can lead to mobility as well. So mobility
Ufuk,
is a.
I'm going to have to ask you to wrap your talk up, please.
Yeah, sure.
Well, 1 or 2 sentences of conclusions.
Okay, yeah. So the multi-radio nodes are the new the area which people are working on, and it can give lots of capabilities network. Thank you. I'm happy to answer any questions you have.
Thank you very much. Thanks ever so much, Ufuk. Questions from the floor, please. I'm not seeing anything in the Q&A, so unless somebody's typing or while somebody's typing, I'm going to ask you a question.
Yeah, sure.
When people talk about industrial Internet of Things and wireless sensor networks, they are quoting numbers of hundreds of thousands of devices and millions of devices. The largest deployment I've seen of anything like that using the network stack that you were discussing in your talk was in the region of 100, 150, maybe 200 devices. So I was wondering, what are your thoughts about the scalability of the protocols in the particular network stack that you are addressing your research? And I'm thinking mainly Ripple, Tish, and 6LoWPAN.
So in terms of MAC layer, the scalability is a bit limited due to the number of channels we can use on 2.4 gigahertz, which is 16 channels we use. So when the frames are processed, which are getting close to the sync radio, which is gateway kind of, so we see lots of drops. So we can't scale the network a lot because of the limited number of channels and the time slot. So what we do is we give extra bandwidth using sub-gigahertz radios work in parallel with others, so you can scale the network even bigger using that main backhaul connections with multi-radios.
Okay, thank you very much, Ufuk.
You're welcome.